Welcome back. Today we'll briefly review vectors and some of their important properties. A vector can be defined by 2 points in Euclidean space. We distinguish between the vector v, which represents a physical quantity, and the column matrix v of its components in a specific coordinate frame of reference. A vector, such as this one, has magnitude and direction and can be represented by an arrow. Two vectors add by the parallelogram rule. So if this is vector A and this is vector B, their sum, A plus B, is this vector. Vectors have 3 components in 3-dimensional space for a given coordinate system. For example, with the coordinate system with origin O and unit vectors e1, e2, and e3, the vector A can be written as A equals a1 e1 plus a2 e2 plus a3 e3, or using index notation and the summation convention, ai ei. The matrix A, a column matrix, is the matrix of the components of the vector. Note that the matrix does not include the coordinate system, so the matrix is not the same as the vector. The vector is the components and the coordinate system. With a different coordinate system, there would be different components. The magnitude of a vector A is defined by a squared equals ai ai. This is Pythagoras. So a squared equals a1 squared plus a2 squared plus a3 squared. A particular vector is a position vector, x. The position vector of a point P has components that are coordinates of that point P and a magnitude that is length of the line OP. The position vector is an unusual vector. It's the only vector whose components depend on the origin. For this reason, it's sometimes referred to as a pseudo-vector. Now, you're familiar with operations on vectors, such as the scalar or dot product of 2 vectors, A and B. For example, if A and B are here separated by an angle theta, then the dot product or scalar product of A and B is A dot B, which equals AIBI, and is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. Therefore, as A is parallel to B, the dot product of A and B is the product of their magnitudes. And if A is perpendicular to B, then the dot product is 0 and the vectors are orthogonal. For example, if we take the dot products between all of the base vectors with each other, then we get ei dot ej, which is delta ij. That is, when ei is dotted with itself, e1 dotted with e1 is 1, e1 dotted with e2 is 0. So every time a unit vector is dotted with itself, you get a 1. Every time it's dotted with one of the other unit vectors, you get a 0. So therefore, in general, ei dot ej is equal to delta ij, the Kronecker delta. Now let's look at the vector or cross product between 2 vectors A and B. The result is a vector that's normal to the plane of A and B. And we compute the cross product by computing the determinant of the following matrix, the matrix containing E1, E2, and E3 in the first row, A1, A2, and A3 in the second row, and B1, B2, and B3 in the third row. And in index notation, this can be shown to be Eijk, which is the permutation symbol, times AJ times BK times EI. The dot product of a cross product and a vector is called the scalar triple product, A cross B dot C, and is therefore a scalar, and it is equal to EIJK AI BJ CK. Note that all of the indices here are dummy indices or repeated indices, so that there's no free index, and therefore the result is a scalar, which we would deduce because the cross product is a vector, and a vector dotted with another vector is a scalar. Now let's look at what happens when we change the coordinates. Now a vector is independent of observer. It's a physical quantity, and it therefore must be independent of the coordinate system or frame. So when the coordinates are changed, the vector components must change, not the vector itself. Now, with the exception of the position vector, the vector components will be unaffected by a translation of the coordinate axes, i.e. a change of the origin from, say, O to O prime. Now, if all observers agree to use a right-handed Cartesian reference frame, and given that a translation of the reference frame, a change of origin alone, has no effect, then a new set of unit vectors can only be a rotation of the original set of unit vectors. Let's consider the vector A with components AI in a coordinate frame with unit vectors EI, and components AI bar in a different coordinate frame with unit vectors EI bar. Now, since by definition the magnitudes of EI and EI bar are 1 because they're unit vectors, then the dot product between them, EI bar dot EJ, would equal the cosine of the angle between I and J. And since there are 9 combinations, this would be a matrix of angle cosines, where you can think of the components of that matrix as the components of the new unit vectors EI bar referred to the original coordinates EJ. In other words, we can write that EI bar, the new unit vectors, have components Mij with respect to EJ. Now, EI bar are also mutually orthonormal, meaning they're also orthogonal and have unit length, just like the original unit vectors. So therefore, EI bar, EJ bar dotted together must equal delta ij, the Kronecker delta, just as it was for EI and EJ. And using this expression here, that gives us MIK EK dotted with MJL EL, which is rearranging this MIK times MJL times EK dot EL, which is delta KL. Delta KL just turns K into an L or L into a K, which simplifies to MIK MJK, or equals delta IJ. Or, in matrix notation, M times M transpose equals I. In other words, M, which is the matrix of components Mij, the angle cosines, is an orthogonal matrix. It's a rotation, just as we originally posited. Now, this is true provided that EI bar and EJ both have the same handedness. In that case, the determinant of M will be positive 1, and then M is said to be proper orthogonal. If the handedness switched, then the determinant would be minus 1, and it would no longer be a proper orthogonal matrix. So we've seen that a vector is the same physical quantity regardless of the coordinate system used to measure it, but it will have different components for different coordinate systems. Recognizing that a translation doesn't affect the components of a vector, and assuming that everyone is using a Cartesian frame of reference with the same handedness, the only difference between one frame of reference and another is a rotation, which is an orthogonal transformation. And so we can now go on to use that orthogonal transformation to define the relationship between the components of the vector, given that we now know the relationship between the unit vectors of the two coordinate systems. So we'll do that next time.